pipings and out into the system. In order to follow the flow of the steam through the system, we will use as an example a basic one-pipe steam system. Let's begin at the boiler and the call for heat. The burner ignites. Water in the section waterways is heated, producing steam. The steam travels up through the water and collects in the steam chest, travels through the upper port openings to the supply riser, into the system header, and on into the supply main. The steam travels through the supply main to the radiator risers, constantly pushing air ahead of it. The steam enters the radiators, pushing the air out through the air vents. Once the steam contacts the air vent's heat-actuated float valve, the air vent closes, forcing the steam to remain in the radiator. Turning into condensate, the steam gives up its heat to warm the room. The condensate begins its return to the boiler, flowing down the same pipe from which it entered the radiator, into the return piping, and back to the boiler. Now, before we look at the steam boiler controls, let's take a break and review what you've learned about steam boilers and the generation of steam for heating. Turn the videotape off now and complete Section A of your workbook. You should now have a very good basic understanding of how steam is generated within a steam boiler. Next, it's important to look at the controls and safety devices that distinguish steam boilers from other types of hydronic heating. These include a steam pressure control, pressure gauge, water column gauge glass, steam pressure relief valve, and low water cutoffs. Controlling the cycling of the steam boiler is the job of the specially designed steam pressure control, often referred to as a pressure troll. Many steam pressure controls have two settings: low, or burner on, and a differential setting. On this pressure control, the low setting might be set at 1/2 psi, pounds per square inch. And the differential set at 1.5 psi. This would mean that the pressure control would cause the burner to stop operating at 2 psi, which is the low setting plus the differential setting. This can be referred to as a pressure control with an additive differential. Some pressure controls have a high or main setting rather than a low setting. For this same example, the high setting would be 2 psi. The differential setting, 1.5 psi, making the low 1/2 psi. This is called a pressure control with a subtractive differential, since you subtract the differential setting from the high setting to arrive at the low setting. In this example, the burner would come on at 1/2 psi and go off at 2 psi. The pressure control is piped into the boiler through a pigtail siphon. The pigtail siphon acts just like a trap in a plumbing application. It contains a water seal. That prevents the pressure switch from coming into direct contact with the steam, which, due to high temperatures, could cause premature failure of the switching device. On a semi-commercial or commercial steam boiler installation, a P-trap siphon is required rather than the pigtail siphon. When pressure in the boiler drops below the cut-in setting, the switch connection to the burner closes. And if the thermostat is calling for heat, the burner responds with ignition and fire. Steam pressure is generated within the boiler, and the steam flows through the system. When the cutout pressure is reached, the switch to the burner opens its circuit, shutting off the burner until the pressure again drops to the cut-in setting, igniting the burner again, continuing to cycle until the call for heat has been satisfied. Steam boilers have a steam pressure gauge rather than a water temperature gauge found on water boilers. This gauge gives pressure readings in PSI, pounds per square inch. Notice the gauge is connected through a tapping located above the water line. All steam boilers provide for visual observation of water level in the boiler with an externally installed water column gauge glass assembly. This gauge glass is mounted to the boiler through tappings so that you can see the operating level of the water within, providing for a visual inspection against running the boiler with too little or too much water. Not enough water in the boiler can affect the steaming action, and in some cases will cause major damage to boiler sections and the burner. If the boiler has more water than required for normal operation, surging could occur, forcing water out of the supply tapping into the header and system mains, restricting the efficient flow of steam and creating water hammer. On or near the top of the boiler, you'll find the steam pressure relief valve used to protect the boiler from excessive pressure. This is similar to the pressure relief valve on a water boiler. However, the steam relief valve relieves excessive pressure all at once. For cast iron steam boilers, these valves are set to discharge at a maximum of 15 psi. All steam boilers are required by code to have an automatic low water cutoff. Now, this safety device automatically shuts the burner off when the boiler water level drops below water level control setting, and restarts the burner when the water returns to a safe operating level. Let's examine this cutaway of the McDonnell & Miller No. 67 low water cutoff. It's used on a Weil McLain Model 68 oil-fired steam boiler. Now notice there's a mark cast into the body of the low water cutoff. It indicates the shutoff level. Now this mark should be 1/2 inch higher than the lowest visible point in your gauge glass. Now when the water falls to this mark, the burner is shut off. To get the burner back on, the water must be raised 1/2 inch above the mark. Low water cutoffs require periodic maintenance to rid the float chamber of sediment that can collect and cause a low water cutoff to be inoperative. Periodic flushing or blow down of the float chamber is recommended during the heating season. In a new installation, a daily blow down is recommended for the first couple of weeks. It's to make sure the low water cutoff float chamber is clean due to sediment that can break loose from the old piping and collect within the boiler and the low water cutoff. One other type of low water cutoff you might come across is a probe type. Now this type of control should only be used with boilers that have a tapping provided for it. Now this probe is inserted into the boiler through a tapping. Again, it is wired to control the burner. Now, the probe completes an electrical circuit through the water to ground when it is submersed in the water. When the water level drops below safe operating level, the probe is located so it no longer touches the water in this condition, and the electrical circuit is broken, signaling the burner to shut off until the water level returns to a safe operating level. This type of low water cutoff usually has a timer built into it to allow for normal fluctuation of the water level during normal boiler steam generation. This type of low water cutoff doesn't need to be flushed. since it doesn't have any place for sediment to accumulate. However, deposits can build up on the probe and allow the electrical circuitry to remain on in a low water condition. As a result, the probe should be removed and checked annually, and should be checked more frequently in a hard water condition or when a high percentage of makeup water is used. On some steam boilers, you'll find a combination of low water cutoff and water feeder, or pump control. In this case, the low water cutoff operates as we've already discussed. In addition, should the boiler water level drop below the established setting, the float in the water feeder will drop and open a valve, allowing makeup water to enter the boiler, stopping when the feeder has returned the boiler to safe operating water level. Please note, Weil McLain does not recommend the use of a water feeder in supplementing the slow condensate return. This could cause too much water to enter the system that could lead to flooding of the boiler, water hammer, and premature failure of the boiler due to oxygen corrosion. It's important to note that if feed water is needed because of the leaks in the system, the leak should be found and properly repaired. Having discussed steam boiler controls, pressure controls, the water column gauge glass, pressure gauge, steam relief valves, and low water cutoffs, we're now ready to look at the piping around the boiler. Before we do, though, turn the videotape off. Take a few moments to review the steam boiler controls, and then complete Section B in your workbook. We now know how a steam boiler operates, some of its components, and how it heats a home. Let's look at the piping around the boiler known as near boiler piping. This piping should always be considered part of the boiler unit, since it is critical to assure proper steaming. Therefore, if you replace a steam boiler, the near boiler piping must be replaced as well. We'll begin with the supply tapping. On most Weil McLain boilers, the tapping, or tappings, will be on the top of the unit. However, on some boilers, the supply tapping may be found on the face of the sections rather than the top. The boiler risers are connected to the header. It is important that the header be sized per manufacturer's instructions, never less than the recommended size. You must also allow a minimum of 24 inches between the boiler water line and the header center line. Anything less than 24 inches increases the chances of water hammer and insufficient or wet steam. When you are installing a boiler with multiple risers, you should install offset piping from the risers to the header, which are commonly called swing joints. These swing joints accommodate the expansion and contraction of the piping in the boiler. The header piping will have a higher rate of expansion than the boiler. Therefore, the swing joint piping system protects the boiler from external forces of expansion. When the boiler is steaming, the header will expand more than the boiler. Here, the expansion forces are exerted against the elbow connections to the boiler risers. Swing joints provide protection against cracked and leaking fittings and boiler sections. At the far end of the header, notice there is a reducing elbow with the small end looking down. This is tied into this vertical pipe called the equalizer. The equalizer's purpose is to allow condensate from the header to immediately return to the boiler, providing for drier steam in the header and for equalizing the supply pressure in the return pipe to the boiler. So boiler water doesn't get pushed back through the return piping as the steam pressure increases. Always reduce the header after the vertical drop into the equalizer. Never reduce in the header. This would result in a water trap without any place for the water to go. Water trapped in the header reduces the effective diameter of the header, forcing steam flow through a smaller opening and at a greater speed. The speed or velocity of the steam can carry water out into the system, causing water hammer and an immediate reduction in water level. Again, consult manufacturer's instructions for proper header and equalizer sizing. In piping multiple boiler risers into a common header, the system takeoff riser must be between the equalizer and the closest boiler riser to the equalizer. This arrangement allows for the most efficient flow and separation of steam and condensate. The steam should always flow toward the equalizer. On a single riser boiler, add a T in the header for connecting to the system main between the supply riser and the equalizer. In piping multiple system takeoff risers, it is recommended that they are all piped out of the header, again between the equalizer and the closest supply riser to the equalizer. This arrangement should never be used. What you are creating here is a bullhead T, where the steam will crash into this T, causing violent disruption of the steam flow called water hammer. Water hammer can be potentially damaging to the piping system and can cause improper steam and condensate flow, along with annoying and undesirable noises in the pipes. Returning to the equalizer, notice it is connected to the boiler's return tapping and that there is a T in the equalizer, 2 inches below the boiler water line. Attached to the T is a short or close nipple which ties into the condensate return of the existing piping system. This creates what is known as the Hartford loop. The Hartford loop was developed by the Hartford Insurance Company in the early 1900s as a means for keeping water in the boiler under steaming conditions, or in case of a break in the return piping. Prior to this, the common solution was to add a check valve in the return just before the return piping went back into the boiler. The problem with this was that it would fill with dirt and scale and stick open, draining the boiler. Today, you may still find check valves used for the same purpose. It is highly recommended that they be removed and the proper near boiler piping be installed. Weil McLain recommends that a Hartford loop be installed on all their steam boilers. If we look at this example, we can see from the water levels in the boiler and at the short nipple that the boiler pressure at the water line and the pressure at the short nipple are equal due to the equalizer line. If the water line drops to the level of the short nipple, no more water can be forced from the boiler. Or if there's a break in the return, the boiler can't be drained. Also notice, any condensate accumulated in the header is returned to the boiler through the equalizer. When configuring a Hartford loop, it is essential to use a short or close nipple at the T connection to minimize water hammer. Also, the short nipple must be installed 2 inches below the boiler water line, or on larger commercial boilers, 4 inches below the boiler water line. This last pipe is the cold water fill pipe, which is tied into the condensate return piping below the water line and as far from the boiler as practical. This allows the cold water to mix with the warmer condensate before entering the boiler, thus preventing any unnecessary cooling action in the boiler, which could result in the complete collapse of steam. We should now understand near boiler piping, the supply tappings, headers, equalizer lines, and the Hartford loop. Let's take a few moments to review this material. Turn the videotape off now and complete section C in your workbook. With our understanding of near boiler piping, along with the purpose and need of each pipe, let's now take a look at what system piping consists of and the significance of its elements. We'll begin by examining a basic one-pipe system. Notice that the near boiler piping is connected through a T in the header into the system riser, then tied into the existing main. The steam travels from the header through the system main to the radiators, which are connected off of the main. In this example, the main also carries the condensate back to the return. Notice that the condensate flows in the same direction as the steam in the main. When examining the system main, you should make sure it has proper pitch to eliminate possible cause of improper radiator heating, water hammer, and for proper return of condensate through the force of gravity back to the boiler. The pitch should be at least 1 inch per 20 feet. To check this, measure down from the ceiling from where the main begins to where the main drops into the wet return, measuring from the ceiling because it is generally more level than the basement floor. At the end of the main, there should be installed a quick vent, sometimes called a main vent. The quick vent rapidly expels air out of the main, allowing the steam to travel faster for more equal steam distribution and for quicker and more efficient heating. Many older steam systems don't have a quick vent or have one that's not properly operating. In any event, it's highly recommended that one be installed or the old one be replaced. The quick vent should be installed at least 15 inches from the drop into the wet return. And for the most efficient operation, should be located 6 to 10 inches up on a nipple above the dry return.